Today's two lessons are going to be experimental probability on the front and then two-way tables on the back. And they actually go together really well because a lot of times you'll be finding your experimental probabilities from two-way tables. So it's actually a good thing that we're learning them together. A little bit of vocabulary first. Probability. So when someone says, what are the chances of that happening? They're saying the probability. You know what they're not saying? Odds. Odds are not the same as probability. So let's not use that terminology. We will not be doing odds because we are not gambling. Now, should you like to write an IA on gambling? Awesome. I would love to read one. Then you could use odds, but that's not what we're talking about. We're talking about probability. Some vocabulary for you. The number of trials is the total number of times an experiment is repeated. Should make sense. I'm going to roll this die 16 times. That's 16 trials. Outcomes are the different results that are possible for a single trial of the experiment. So if I roll that die, there are 6 possible outcomes. Frequency, we already know what frequency is, but the frequency of an outcome is the number of times an outcome is observed. Now, relative frequency, I don't remember if we talked about that or not, but relative frequency means it's frequency relative to the whole system. So see how they say it. Relative frequency is the frequency of an outcome expressed as a fraction or percentage of the total number of trials. And that's what I mean by the whole system. So if I roll that die 16 times and I see a 5 come up 3 times, it has a relative frequency of 3/16. 3 out of 16. Well, guess what that would have been? Because I just described the results of my experiment, experimental probability is equal to relative frequency. It's not any really groundbreaking stuff. Don't worry, it's not some kind of tricky IB thing. It's really quite simple. It's not the same as theoretical probability. I mean, theoretical probability is, in theory, how should that have happened? Well, in theory, I should roll a 3, 1 out of every 6 rolls. But it doesn't always happen. In theory, it would, but, experimental probability is what did you actually observe happening? A small plastic cone is tossed into the air 279 times. It falls on its side 183 times and on its base, meaning the circle, 96 times. That doesn't add up to 279. Yes, it does. I'm so tired. Oh my gosh. Wow. Okay, anyway. I was just like, wow, that's a colossal mess up. But no, it does add up to 279. I'm so tired. Question says, what is the total number of trials? You would say 279. And so we'll say n equals 279. We often use the letter n to represent the number of trials. When you're reading studies, and it's always important that you know what n equals, when you're reading studies, when they're like, oh, this just in, drinking water causes cancer. Well, somewhere in parentheses in the abstract of the article, there'll be an n equals, and it tells you how many people they studied. And if you pay attention, sometimes it's like n equals 9. You're like, whoa, 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 whoa. You just base this whole paper off of 9 people. You can't, so it's important that you understand the statistics here. What are the outcomes? What are the possible outcomes? Well, not how many, that there are 2 possible outcomes, but what are the possible outcomes? Sides and base. So side and base. So there's only 2 possible outcomes. When it says what are the frequencies, that means how many times was it observed, not the probability. So the number of sides was 183, and the number of base, so when you say n of, that means number of. It's not a function, it's just, that's how probability is written. So up at the top where it says n equals 279, that is not the same n that you're seeing here. Well, if you just say n equals, that means how many trials were there. But we say n of, that means the number of times this outcome was observed. The number of times that base was observed is 96. Now when it asks for the relative frequencies, that is the probability that it happened in that experiment. So the relative frequency would be written as P of, and I'm kind of jumping the gun a little bit on this kind of symbols, but this is how it looks. So P of side, that means probability of side, is 183 out of 279. And you would turn that into a decimal, but I'm not remember if I did or not. Let me take a peekaboo at the old notes here. Because probabilities can be represented as decimals, fractions, or percentages. It's not really important which one you choose, unless of course they dictate a certain version to you. So if it says what is the percent that happens, or what is the probability that it happens, those are two different questions. You know, what percentage of yada yada yada, that had better be a percent. If it just says what's the probability, you can either leave it as a fraction or you can move it to a decimal, and I did write this as a decimal just in case. 3 sig figs is 0.656. And the probability of it landing on its side is 96. I'm sorry? Yes, base. Probability that it lands on its base is 96 out of 279, which is about 0.344. Hey, what do you get if you add those two decimals together? 1. That should make sense. Because when you toss this cone into the air, there is absolutely no way it's going to land on anything other than its side or its base. It's not possible that it lands on the tip. That's just not possible.
Why not?
Because it's impossible. It wouldn't matter if there's millions of trials, it's still impossible. The table below shows the number of short-term visitors coming to Australia in the period of April to June of 2018 and why they went there. So we got convention or conference, business. I'm not really sure how those two things are different, but hey, there it is. Maybe you're like selling something, okay? Business, visiting friends and relatives, a holiday, and by that they mean vacation. Remember, this is international. A lot of the world calls vacation holiday. Employment, meaning I went there because I got a new job. Education or other. Great. So we have the number of people for short-term visitors coming to Australia during April, May, and June of 2018. And it says estimate the probability, and this I'm going to have to grab a calculator because this is a brand new example. Estimate the probability that a person who visits in June is on holiday. So it said the probability of June, you know what? I'm not going to show you those symbols. Let's just write the answer, and I'll explain why here in a minute. Estimate the probability that a person who visits in June is on their holiday. So where should I be looking? Estimate the probability that a person who visits in June. So you need to be looking at the June column. And so we're trying to figure out the probability that a person who visits in June was on their holiday. So now you look to the number of people that were on their holiday out of the number of people that were there for June. So it is going to be 156,500 out of 300. So this is the probability that someone visited in June knowing that this is the probability that they're on a holiday knowing that it's June. It's two different things. Order matters. Probability someone is on their holiday, on vacation, knowing that they're in June. And time to do some calculations. 156,500 divided by 308,300. About 0.508. That's 3 sig figs. So a little bit more than a 50% chance. A little bit more than a 50% chance that people that were visiting in June were there for vacation. Gee, I wonder why. Because it's winter there. So it's hot as crap elsewhere, but there it's winter, so it's not so bad. Because winter in Australia is probably like 70 degrees or something. Reverse snowbirds. They are lava birds. Firebirds. Oh, firebirds. Oh, that's so much better than what I said. Okay. Okay. Estimate Estimate the probability that a person who came to Australia during this period of time came in May. Oh, what would we need to know in order to pull this off? We would have to add all the totals. We don't know how many people actually showed up during that period of time, do we? So let's add these totals up. 321, 500, plus 260,900, plus 308,300. That's a lot of people. There's 8,90700 total people. Estimate the probability the person who came to Australia during this time came in May. So the people who came in May, 260,900, divided by the total number of people who came at all, 890,700. It is a number, about 0.293. So that tells us about 29% of the people who came during April, May, and June, who came during those 3 months, about 29% of them came in May.
Why is it that in the period of April to June?
Because this entire table is April to June. So the whole table is April, May, and June. So basically what it just asked us is what percent of the people came in May. That's what it says. But it said it in a weird way. Well, not if it had said percent, we would have said 29.3%. But instead it says what's the probability, so we left it as a decimal. Part C, is this the last part? Lars arrived in Australia at some point during the period shown in that table. So Lars got there sometime April, May, or June. We're just not sure. We want to estimate the probability that he arrived in April. Yep. So the probability that he showed up in April was 321,500 over 890,700. Yeah. So basically it wanted to know what's the probability someone showed up in April. The whole fact that it was Lars doesn't really matter. They could have just said, what's the probability someone came in April? They could have said it just like that, but you know they're going to mess with the words. So 321,500 divided by 890,700, about 0.361. So about 36% of people showed up in April. What do you think about that? Yeah. It's not too bad reading data off a table, right? Yeah. Yes, there is. But that was all of the notes for the first lesson. It's legitimately just like, hey, look at what happened and find probabilities from reported data. Now, often there could be a lot of results. So often data will be represented in a table of outcomes. Like you just saw, April, May, and June was actually a table of outcomes. And I could have asked a lot of different questions from that table. Well, the book could have, I didn't make those questions up. But it would have required a little bit more effort on your part. These are called two-way tables. Tables of outcomes are tables that compare two categorical variables. That's why they're called two-way tables. These tables are often a result of a survey, like you just saw, and they can be used to estimate probabilities about entire populations, I'd say as long as the number of trials is large enough. People exiting a new ride at a theme park were asked whether they liked or disliked this ride. And those results are shown over there. So we have 4 different options. You could either be a child or an adult, and then you either could have liked the ride or disliked the ride. Okay. Let's see, do I have these for me? Yep, there they are. So in order to pull off a two-way table style question, it would be very, very useful to have a total column and a total row. This is very useful information. So before we even try to answer the questions, We want totals. Yep. So in the last question, the only total we actually used was the total number of people because they provided us with the total of April, the total of May, and the total of June. But usually a two-way table will be missing the total column and the total row. So you would need to find that information. And you do that just by adding. So this should be 83, 47, 130. 72 and 58. There. And we can now use this table to solve for these probabilities. I'm just scrolling down. So that's all that's on this side. Awesome. Oh. See, what we're finding here is actually called conditional probability. And conditional probability will be its own section of notes in the near future. I don't know when your chapter 2 test is yet because I haven't even finished making the notes for the chapter. I don't know how long they're going to take me to get through. I literally only have you through this week. That's all I have done is through this week.
Slacker.
Yeah, I'm slacker, he says. Anyway, so this is going to be a day-by-day, week-by-week basis. I'm sorry. Here's what I do know. The section's going to have a minimum, or the chapter's going to have a minimum of 11 sections. We're going to get 5 of them done this week. I suspect that we can get 5 done next week, which would mean the following week, the test will land in there somewhere. Oh. Also, Spirit Week is only 4 days long. You guys know that, right?
Yeah, so like we should, can we do like
So anyway, hopefully that test lands in Spirit Week. That way everybody's in good spirits for their test, yes?
How do teachers have 2 like professional or work days now?
It's also for deep cleaning.
Is it October 13th that we're on?
I don't know what the dates are. I don't remember.
What are they gonna do? What?
Do they have an official list of the Spirit Week days?
They just spray these boards,
Yeah.
they just like them.
Okay, so the first question, question A says, what's the probability that someone who's polled liked the ride? So my question is what is the denominator of the fraction? So yeah, the probability that they liked it, this is out of the entire population. So this is going to be out of 130. But what's the numerator? 83. Good. And that is about 0.638. Yeah, so almost 64% of the people like the ride. Probability, or part B. Probability that a person who's polled is a child and disliked. So it's a child and disliked. My question is, what is the denominator? It's still 130 because I'm talking about I reached into a crowd of random individuals and I'm wondering, which by the way, there's 130 of them, I'm wondering what was the probability that the person I pull from the crowd is a child that disliked the ride. So 17 out of 130, which is about 0.131. Part C, adult or disliked. Probability, wow, that P is a little pointy. Probability of adult or disliked. Now this one is a little more interesting. Denominator. 130 still. Now the numerator, rather than saying what it is, you say it's 75. How did you get that number? Add the adults, which is 58. And then?
You add the dislike the ride, but then you subtract 30 because you already had the adults.
Okay, you did that strangely, but you're not wrong. Rather than do it that way, I'm going to explain it a little bit easier, okay? So let me first of all, have you studied probability somewhere before? He common sensed, hey, 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 he common sensed his way to the right answer, but no, so here's what happened. Explain to the class why you subtracted. You said you added some numbers and then you subtracted something. Why did you subtract it?
It's asking for the total adult and dislike.
Yeah.
The adults are counting the dislike.
Ah, because if we had added up the adults and the dislikes, we would have double counted the adults that dislike. Good. Yes, but what I'm going to do is I'm going to add up, I'm just going to look at the table, and if one of the 4 original spaces is a yes, I'm going to put it up there. So adult, 28, and then another 30, and then the only other box that works is the 17. Okay. Anyway, so this is going to give us the 75 over 130. What you were doing, and Harrison, you probably didn't know it. You were subtracting overlap, which is going to be very, very important here in the near future when we start talking about compound events. But for now, when it says or, just make sure you don't double count something. That's all we had to do. So I just like, oh yeah, this one, and this one. All 3 of those satisfy. And that number is 0.577. If you can get there more than one way, epic. D. Trying to find the probability that someone liked the ride, given that he or she is a child. Aha. Now we're working into conditional probability. See, I gave you a condition. Given that, and it could be, this is English, the sentence can be rearranged without changing the meaning. Given that someone is a child, what is the probability they liked the ride? So what did you do now? You said, what did you say? So why did you choose the denominator of 72? Right. Because it said given that you were looking at children, well, the secret is whatever information is given will be your denominator every single time. So if I say given that it's a child, oh, okay, I can only look at the children here, the column of 72. And then we said, what is the probability that they like the ride? And you said 55. Good. See, what this tells us is about 76% of the kids like the ride. That's important information for a theme park, right? They go, ooh, kids like this ride. Now what we want to do is say, well, okay, the probability that someone is an adult, given that they disliked the ride. So what is the denominator now? 47. Because I said given that disliked the ride. So the total for dislike goes on the bottom, and this is probability that that person is an adult. 30 out of 47 gives us 0.638. So what that tells us about 64% of the people who don't like this ride are adults. So it's probably a kid's ride because we found out that 76% of the kids do like it. And that is the entire note set, for today at least.